Hi guys, it's a short talk on poster session V21, and what I'm going to tell you about is estimating entrainment rates by ocean currents based solely on changes in sea surface salinity. And as an example, we're going to use the Erminger current. Let me start off by telling you the results. What we do is we define a new schema called freshening length that quantifies sea surface salinity changes or gradients in sea surface salinity. We use it to find the ratio between two important parameters in ocean currents, the flux of the current itself and the rate at which it entrains the surrounding water. Entrainment rate is very hard to measure directly, and this sea surface, this freshening length schema will help us greatly. As an example, we're going to use the Erminger current that flows east and west of Greenland. So let me start off by showing you the paradigm that we use. We envision a high salinity current that flows in a fresher water ocean. The depth is about H, and the salinity of the salty current is higher than the surroundings, so it's S1, but it decreases as we go downstream because of the entrainment of the by the current of the surrounding fresher water. So the current has a speed of U, depth of H, and it entrains water at an unknown rate. And the two elements that are important here, that due to the entrainment of water, there is a salinity gradient along the current, and we can construct a parameter whose dimension is length by taking the salinity, mean salinity in the current, divided by the salinity gradient along the current. And this is the freshening length that we identify. And when we have the freshening length, what we can do is take the entrainment rate and show, again, I'm not going to go into it, that the entrainment rate of the surrounding water by the current times this freshening length is exactly the flux per unit length in the y direction, in the cross-stream direction. Just two comments. The length of the transect should be short compared to the freshening length, so the ratio should be much less than 1 for the linearized theory to be valid. And on the other hand, X to be large enough for the S, for the salinity changes to be observable. So they are not too small that we cannot quantify them. So I'm going to apply the concept to the Erminger current. So a few words about the Erminger current. It branches off from the North Atlantic current, which is just a continuation of the Gulf Stream. It carries out as such warm and salty water into very high latitude. You see that it approaches nearly the polar latitudes. And it flows in our area of interest east and west of Greenland, and somehow the current negotiates the southern tip of Greenland, Cape Farewell, and continues into the Labrador Sea, not all of it, probably part of it. The current is clearly identified by a local salinity maximum. And just a note that the intense cooling at those high latitudes of the salty water causes the sinking, or downwelling, which is part of the AMOC, the Atlantic Meridional Overturning Circulation. So we look at surface salinity on the east, marked by blue, and on the west, marked by red, in a transect that's about 700 kilometers long. And we take 37 years of SODA data that are 0.5 degrees in longitude and latitude. At each latitude, okay, we locate the longitude of maximum salinity, east and west of Greenland. And from this maximum, we take 2 points to the east and 2 points to the west, again on both sides, for a total of 5 points averaging of what we call the high salinity current. And then from those averages, we calculate the changes in the downstream direction, okay? Southwestward here and northwestward here on the west side. To begin with, we start with the TS diagram, classical tool in physical oceanography. And you see that on the east side, where the triangles are blue, what you see is that both salinity and temperature decrease, but at a slow rate, and they maintain the same density, 27.4 sigma units. On the west side, salinity and temperature don't compensate for one another, both decrease, but in such a way that the salinity is actually decreasing. And of course, there is a vast difference between the two, and the salinity decreases because it entrains fresher water on the west side more than it does on the east side. So this is a very clear qualitative difference between the two, quantitative difference between the two. The question is, can we do something to quantify it? Can we do some numbers on it? And the answer is that the freshening length is indeed capable of giving us exactly that. So remember that L is calculated from the salinity over the gradient in salinity, S over the SDX, and the linear approximation is very good. R squared of 0.92 on the east side and R squared of 0.97 on the west side. So we can take the SDX to be constant here. And if we take the ratio between them, we find that the freshening length on the east side is about 120,000 kilometers. And on the west side, it's about 22. Okay, so now we have a ratio of about 5.2 between the L's. We can calculate, again, from soda, the ratio in the fluxes by taking the integral of U over H from a very deep level, say minus 1,000 meters or so. And we find that on the east side, the current carries a little more, somewhat more water than on the west, about 1.7. So if you now look at Q, which is equal to F over L, you find out that Q on the west, the entrainment rate on the west, is about 3 times that on the east. If you just divide 5.2, which we found before for L, by 1.7, which we find for F. And the idea, the main conclusion is that the entrainment rate on the west side has to be about 3.2 times larger than that on the west side. Thank you. And if you want more details, you can find them in this paper, and you can also contact me. Thank you very much.